So, friends, today we'll be doing chapter 2 some or other. The important part here is we're going to be looking at the derivative graphs in relation to the function graphs. Okay, so just actually no definition, this just kind of a vibes thing, so we're just gonna get into it. So if you guys remember, I noted, or if you guys remember, right, functions have in the graph they have a couple interesting things. So like, say this is your plane, right, and your graph is like, let's do in a plain color, something like that, right? Some interesting things you might have are like, the y-intercept, if you have those, like some of the x-intercepts, you might have some maxes, you might have some mins, right? Let's do mins in orange, right? And of course, you have the end behavior as well, if it has something that can describe its end behavior. Okay, so given that, we're going to get into kind of understanding the relationship between a function and its graph. Okay, so one thing I'm going to note is one, if f of x is equal to like 3x plus 18, right? Then f prime is equal to 3. If g of x is equal to 3x plus pi squared, remember pi is just a number, pi squared is just a number, then g prime is equal to 3 as well. These two have the same derivative, which means they have the same derivative graph. Okay, that happens. It's very normal, even if these two are not the same. Okay, and two, critical values also apply where f of x has a discontinuity. Okay? Because again, what is the point of a critical value? The point, unintended, of a critical value is where your function might change directions. Right? Okay. Now, I'm gonna exercise this really quickly. Let me start my focus a little silly. Right? Let's say you have f of x is equal to 1 over x minus 1 squared. Right? Then f prime of x is going to be, I'm going to just push it very quickly. It's going to be b derivative a, which is 0 minus a derivative b, right? Minus a, the derivative at the bottom, you got down, leave the inside alone, leave the inside, cool. All over b squared, which is going to equal negative 2 x minus 1 all over x minus 1 to the fourth, which is going to be negative 2 all over x minus 1 to the third. Okay. Okay. Something interesting here. If you graph f of x, right? You should have a function that has asymptote down at x equals positive 1. Let's put positive 1 here, right? And then f of x, let's do it in pink. Should look a little bit like as x approaches negative 1, the function is still positive, and it is divided by a smaller and smaller number. So it'll go something like that, right? This function will never hit 0 on the left-hand side of negative 1. Do you see how this will never equal 0? On the right-hand side of positive 1, so sorry, you have very similar behavior, right? Okay, clearly, very, very, very clearly, right? You see that on the left-hand side, the function is increasing, and on the right-hand side, the function is decreasing, right? Yet the function never hits 0, okay? So once again, if you notice, asymptotes are very important, okay? They also contribute to the critical value, okay? And you'll find that the asymptote can be found both in here and in here, because asymptotes never go away. Discontinuities don't derive out. They don't just disappear, okay, friends? Now, if you were to graph the derivative of this function, right, you know that your critical value is going to be at 1, right? The function doesn't hit 0, so you're not going to graph it as 0, but you make a note of it. There should still be an asymptote here, because, well, there's an asymptote there. I'm just going to separate like that, right? Okay, now, on the left-hand side, your slope is positive, right? And it's getting more positive. Rate of change is increasing, right? So you want it to go something like that, okay? Above the axis, you see, and on this side, it's negative. So you want it to look a little bit like, oh, and it's going from more negative to less negative. So you want it to look a bit like that, or something of that nature, okay? Okay, so loosely speaking, that's how you graph this. This is a funkier function, so I'll do an easier one with you. Let's say f of x is equal to, and we don't even have to give you a real function, we could just give you a graphical function, right? And suppose that your function looks a little bit like, let's do it plain. Let's say it looks a little bit like this, that, and like that, right? Okay. Now, clearly we see something interesting here, right? Let's say this is negative 5, right? There's also something interesting here. Let's call this negative 1. There's a max here. Let's call that 7. There's a min here. Let's call that 8. There's a max here. Let's call it 9. There's a min here. Let's call it 10, right? So when you look at a graph, first thing you should look at is where are the mins and maxes. And the asymptotes, where are the critical values, okay? Then the next thing you're going to do is you're going to determine where is it increasing and decreasing. It's very straightforward. Ready? Increasing from negative infinity to negative 5. Or, yeah, from negative 5 to negative 1, not inclusive. Decreasing. Increasing. Decreasing. Increasing a little bit. Decreasing a little bit. Increasing. Okay? Okay. Now let's graph their derivative. And we will do so by just and friends, please, label your graphs. This is your f prime graph, okay? And then what we're gonna do with all these critical values here, we're going to map those as well, okay? Okay. So at negative 5, slope is 0. Okay. At negative 5, slope is 0. Okay. At negative 1, slope is 0, so -1, slope is 0. At 7, slope is 0. So at 7, the derivative should hit 0. And then so on and so forth. So I'll do that for 8, 9, and 10, right? So 8, 9, and 10. Because the slope of the original function is 0, the derivative graph must also hit 0. Okay? Now is the easy part. What I personally like to do is I like to kind of make an overlay like mentally. So I make a line down just like that, right? And then I make another line down just like that. So I can just kind of separate them like that. Obviously it's not perfect, you see, but that's okay. Right? Again, this is just your sign chart, right? Okay, right here is positive. So positive. It means I'm up here. You're above the graph, right? Positive is above the graph. Here, I'm negative, right? So I'm below the graph. Positive is above the graph. Negative is below. Oops. Positive is above. Negative is below. And positive is above. All right. So now that I kind of section everything off, right? I otherwise do this on my own graphs. I literally just go and draw like lines so I don't lose myself. Okay. So this function is increasing. So it's positive above the graph until it hits 0. So it's gonna whoop something like that. Does it have to be perfect? No. Once it's above the graph, who cares? And then it's negative, so it's below the graph until it hits 0 again. Like that. Or you can draw like that. Or like that. I really don't care. Right? As of right now, it does not matter. Okay. And then it's positive again. And then it's 0. And then it goes like that. And then it goes like that. And then it goes like, sure, why not like that? And then up it goes. There goes that. Ta-da! This is loosely speaking the derivative graph of that. Easy money. Let's do another one. Let's say f of x is equal to 1 over, actually, this makes it interesting. Let's go x over x plus 3, x minus 2. Okay? So in this form, it's actually not the easiest to derive, so I'm actually going to write it as x all over x squared plus x minus 6. Okay? Then f prime of x is equal to b derivative a, which is 1, minus a derivative of b, which is 2x plus 1, all over x squared plus x minus 6 squared. I'm going to simplify this down a little bit. X squared plus x minus 6 minus 2x squared minus x, but just kind of distributed. Yep. All over x plus 2, nope, x plus 3, x minus 2 squared, right? Which we will simplify as negative x squared minus 6. Negative x squared minus 6, yeah? I should have chosen better ones, but it's okay. All over x plus 3 squared, x minus 2 squared, which is going to be negative x squared minus 6, all over x plus 3 squared, x minus 2 squared. Okay? So last time. F from -100. This is the correct function. Ready, ready, ready? This is always positive. This is always positive. Cool. This is also always positive. Because squared is positive, plus a positive is positive. But there's that negative. So any number you put in, just spit out a negative number. You don't believe me? Work out yourself. Okay. So this function looks a bit like, or this derivative specifically looks a little bit like that. And then you're gonna duplicate it. What I like to do is I like to kind of use the sign chart as my base, right? And then just kind of draw around it. And lower that. And lower the opacity. Obviously, you can do this like by hand too, but it's fine, right? Okay. Negative, but respecting the asymptote. Okay. Negative, respecting the asymptote. Look at that. Same here, negative, respecting. You can really wiggle around like that if you really want, okay? Respecting the asymptote, look at that. And negative, respecting the asymptote, look at that. There we go. F prime x. That's it. Easy. As long as you don't make the same mistakes I do, I'll edit all those out. Okay, so now let's do an example of given f prime, draw a potential. Okay, very easy. Ready? F prime. What I'm going to use the graph because if you can do the graph, you can do the polynomial too. Okay, so let's say f prime looks a little bit like let's say it looks a little bit like this, and then it hits 0, and then it comes under, and then it hits 0, and then it goes. It go up, it goes up, and then it goes down. Oh no, it goes up, and oh my goodness, there's an asymptote. And then all of a sudden, it comes back down like that. Okay. If that were the case, then we know that there's a little asymptote right here, right? Nice and light like that, right? Okay, let's get these values, these spaces some names, okay? So I'm gonna call this 1. X equals 1. I'm gonna call this 5, and we're going to call this, I don't know, 8. Sure, right? Okay. What we're gonna do now is we're going to duplicate this. We're gonna shimmy her down, like so. We're gonna get rid of all that, so and we know that there's an asymptote there. There's gonna be an asymptote here, okay? We love our asymptotes. Okay, ready? So what you're going to do is you're going to our graph. From negative infinity to -1, your slope is decreasing. That is decreasing. And then it hits 0. So there is a horizontal tangent line. And then it keeps decreasing. Cool. And you're just going to draw it continuing to decrease. And then at 5, it increases. Cool. So it should go up. Oh, wait, there's a tangent line. Respect the tangent line. And then, oh, look, all of a sudden it's decreasing again. Cool. You could draw like that. You could draw like that. You could draw like that. I don't care. Why? Because look at the graph. It does what I said it should do, right? It is in fact increasing and decreasing. In fact, you could draw like that if you want, right? Okay, decreasing is left to right. Okay, friends, so decrease, going that way. That's it. That is one way you can draw the original function graph.